All right, do you have any homework questions?
3.254.
Isn't that one that we did?
You didn't know.
Okay. Oh, okay. This is a mean-value theorem, so we're trying to, it says a conclusion of Rolle's theorem, that's when the point at the beginning and the end have the same type, right? So we're trying to find what the derivative equals here. Do you have the same question?
Mine's 10x instead of plus 9 instead of plus 1.
So let's see. So we're trying to find any point of the derivative. It says the Rolle theorem, so we don't have to solve the average slope. So because it's mentioned Rolle theorem, right, so we're really just trying to solve whenever the derivative equals 0. So the number one thing is you have to solve the derivatives. Okay. This is a multiplication. We have x in the 3x, we have x in the root of x plus 1. There are two x's. So that's a multiplication. According to the product, take the derivative of 3x plus 1, and then we can keep the root of x. X plus 1. Plus, we can keep the 3x and find the derivative of the root, right? Derivative of the root is 1 over 2 times the root. Okay, so 3x times 1 over root of x, 2 times root of x plus 1. So that's the derivative. We're trying to find where is this derivative equal to 0. So we would grab the equation, which is the derivative. We're setting this equal to 0. So we're trying to find out how many. Wait, this is. So this is still two terms, summation, separated terms, essentially one term on the left. We can move this one to the right, right? If you have multiple terms, then that will be another thing. This is the equation we have to solve. Then you have 1, 2, 3, 3 x's. So to solve the equation, you have to find a way to combine them to get to the point you only have one axis. So we can't move the one term, two term on the left, move one to the right, and then you have this. You will subtract to get the 3x over 2 roots, one to the right, so you have 3 roots of x plus 1. Still on the left, and the other one, if you move it to the right, it becomes negative, so it's negative 3x. And multiply that to the 1, so it's in the numerator. So negative 3x over 2 times the root of x plus 1. So that's what we have after we move it over to the right side of the equation. And then we, right, then you can cross multiply. Or you can call that multiply both sides of the equation by the denominator. If you multiply the right side by the denominator, you will cancel the division and you have negative 3x on the right side. Multiply the right side of this equation by 2 times x. So you will end up having like this. But if you multiply, basically we multiply 2 roots of x plus 1 to the left, and we also multiply 2 root of x plus 1 to the right. And then you can see that when you multiply to the right, they cancel the denominator. That's why I say there's negative 3x left. But this one, if you multiply 2 root of x plus 1 with this one, root times root, that cancel the root stuff, right? Root of x plus 1 times root of x plus 1 is x plus 1. So that you no longer have any roots. So we achieve double purpose. There's no more fraction, and also there's no more roots. So what's on the left side is 2 times 3 equals 6. The root part, roots times roots, they cancel the roots. All you have is x plus 1. Now we have an equation. It's actually degree 1 on the left, degree 1 on the right. Distribute the 6. We have 6x plus 6 equal to negative 3x. And then we add a 3x. You have 9x. We're trying to get rid of the 1 on the right. The reason I'm adding 3x, add 3x on the left, add 3x on the right. And now there's no more x on the right. This one will be 0 after you add the 3x. Plus 3x cancel the minus 3x. Also, plus 3x on the left give you the 9x. So we have, and then, so we achieve one thing that we get rid of one of the x's. There's only one x now in the equation, and then you work on solving it. As long as you have only one x value in the entire equation, just get rid of everything else, and then you have x by itself. So minus 6, you have 9x equal to negative 6. And then we divide it by 9, x equal to negative 6 over 9. They both have 3. This is a negative 2, 3. So let's find the number c in the interval. So that's the only one I've got. Any question? So it looks like all the other ones are actuals. So it's negative 2 or 3, and then we go n, and then n. And that's. Any question? I believe you can confirm this with a picture. Whenever the derivative equals 0 is when it has a horizontal tangent. So y equal to 3 times x and then we don't want the whole thing, we just want negative 1 and so that's the function. You want to display the function, only display the part between negative 1 and 0. You can see that horizontal tangent line. That's at the point of negative 2/3. That's where the tangent line is. So that kind of confirm the calculus that we did. And you know the answer is making sense when we see the picture.
This would be 2/3?
Negative 2/3.
Yes.
Does yours have the same version of it?
No, mine's 10x squared x plus 9, but I just needed the idea where
Okay,
the process, that was really where I solved it.
okay.
Okay.
Any other questions? Right. So that is number 2, but number 4 of the second section. That's the mean value theorem. Started off with question 1, and I did a question 7. So you can find your answer from question 7. This is question 2. Okay. So we're trying to find out the mean value theorem point for this one. It's the x to the negative 1 power. X to the negative 1 power is a fraction. Negative 1 power means negative 1 over x. So because of their division, So we know that this function, this function looks like this. 1 over x. So basically we are f(x) is equal to 1 over x. So f(x) is the y value that affects if x is bigger, then 1 over x gets smaller. So it looks like this. If bigger x has smaller y, smaller x has bigger y. So you can see how it behaves. That's from -1 to 2. This is 1. This is 2. So this is the 1. 1. That's the 1/2. It's x equal 2. That's but you only care about the part that's between the 1 and 2. So if you care about this, your function is actually huge. The x value is the function is being defined for any x value that's not 0, but we don't want a full thing, which is 1 to 1 between 1 and 2, right? Now you can see that we only want part of the function, and we're running like this. Right, so we are looking for that special point where this is slope, and it looks like the slope is dropped down 1 over 2. Slope looks like it's -1/2. And one of the points seem to be going in the same direction as the overall, the average slope. So we want to find the mean value slope, and then we want to find a derivative that has the same mean value slope. Right. So this just want to explain a little bit about the picture, and then we can just start calculating. The question is about mean value theorem. So as you're reading the question, it mentions some special results. You have to think about that special relation. Now the main thing in the mean value theorem is the main thing in the mean value theorem is we're trying to find a special point when the derivative at that special point, we can find the x value essentially. C is actually an x value we're solving, it equal to the mean slope. The mean slope is calculated by, we look like a slope calculation, f of b minus f of a divided by b minus a. So the c that we are looking for satisfies this equation. So if we want to find the c, we first have to figure out, hey, what was that number on the right side of the equation? I would normally recommend calculate that one. If it's a rule theorem, we don't have to do this, because in the rule theorem, this equals 0. Okay? If it's any arbitrary mean value theorem question, you have to calculate this. So let's calculate this one. And if you want to do this calculation, you gotta know what's a, what's b, and what's your function. So in this case, a equal to a and b. The a equal to 1 and the b equal to 2. All right, so we essentially are calculating f of f2 minus f1 over 2 minus 1. Yesterday, I will be trying to calculate what was the actual value for f2, what was the value for f1, because we have a big polynomial. If this thing it takes a lot of calculation, I would prefer to do it some separately. But if this is easy, like this one, is x to the -1 power, then that is 1 over x. If you plug in 2, that's 1 over 2. If you plug in 1, that's 1 over 1. So right now, for this function, f of 2 and f1, it's not a lengthy calculation. So we don't have to do it, we don't have to move it somewhere else to finish a longer calculation. Just directly mention this is 1 over 2. This is a 1 over 1, which really is 1 over 1. This is over 2 minus 1, which is just 1. So the denominator equal to 1. So the numerator ends up being 1/2 minus 1, which is -1/2. 1/2 is smaller than 1. -1/2. And then finish the whole right side of it. Finish that. And now we're going to move on to the next step, which is you want to calculate f prime of c, and what exactly is f prime? So your second step is you gotta know the derivative. The derivative function should be calculated or should be derived from the original function. This is the original function. And according to power rule, you will move the negative one to the front. So the power has the -1. -1 minus 1 is -2. That's essentially -1 over x to the power 2. It's -2. If the power is negative, it goes in the denominator. So that's what the derivative is. To finish that part. And then lastly, let's try to find out the derivative. So the last part of it is set them equal. So step 3, we will set a -1 over x squared to equal to the -1/2. So whatever you had in step 1 is preparing for the right side. What you were doing in step 2 is preparing the left side. The last thing to do is to have that equation, because only when you have an equation, you can solve it. So we're setting them equal, and then left side and right side both have a negative. We'll set we'll cancel the negative, and then you have this. Cancel the negative and reciprocal, you get x squared equal to. This is the thing about solving an equation. If the equation is equivalent on left and right for the most part, and then the only part that's not equal, you're going to have to set it equal, right? In the left side, if we have a negative, there's a negative. If we have a 1, there's a 1. So you both have -1. And they have, this has a 2 in the denominator, and this has x squared in the denominator, because it's an equation, so the denominator has to be equal to 2. So with the fraction equal to another fraction, they have the same denominator, they have the same numerator, and they also have to have the same denominator. So we have x squared equal to 2. What was the solution then? If x squared equal to x is square root 2. Okay, yeah, that's right. Theoretically speaking, there should be 2 solutions. X is equal to positive or negative root of 2, but we got an interval, right? You can't go outside the interval, so x has to be positive root of 2 because the -1 is not in the interval. So the answer to the question will be square root 2. That's the question number 2. You might not be, do you have the same?
Yeah, I already solved.
Right. Okay. That's why you were working on number 4.
Yes, I just, when number 4 is the only one I had.
Let's try one more question. So I think it's okay. The first derivative is simple enough.
Yeah, all of these are like
Right. You're trying number 3. Any question with it?
I'll make them solve it.
Right.
I needed to do the logarithm thing to cancel.
Right.
So
Okay.
I like remembered, I was like, not again.
Okay. Yeah. So normally we learn from our own mistakes.
Log 3. That was not question 3?
Yeah, that's question 3. Yeah.
Like logarithm of 32 divided by -1. Like this.
So we would run the same process. We would calculate f of b minus f of a. That's the step 1. Divided by b minus a is this interval. This is a. So a is 0 and then b is 8. So this calculation gives us f of 8 minus f of 0 divided by 8 minus 0. Numerator 8 minus 0 is 8. Numerator is, this is our function, so we follow that function for the calculation. So it's e to the negative 8 times 8, so e to the negative 64 minus e to the negative 0. E to the negative 0 equals 1, so that's e to the negative 64 minus 1/8. That's step 1. Step 2, we will calculate the derivative. Derivative of the function would be f prime of x is equal to, this is the exponential function, derivative is e to the negative 8x. The exponential function is the exponential function. Also have to multiply the derivative inside function, that's negative. If you write a little bit nicer, you have negative 8 to the front multiplied by e to the negative 8x. So that's step 2. Step 3, we're going to set them equal because we're supposed to solve a special value that this derivative equal to this special value. So in step 1, we're calculating the mean value. In step 2, we're calculating the derivative. In step 3, we'll set them equal to find out when does a derivative equal to that value. So we're going to have an equation we set negative 8 e to the negative 8x equal to a to the denominator e to the negative 64 minus 1. Right, so that's the equation. It looks complicated because there's a lot of number in there, but if you try to zoom in, we're trying to find the x value. So all the other one, they're really numbers, so we can just to get rid of the number have x.
That number is negative 1/3. Just simplify it further.
E is a special number, so I have to use my calculator to do that.
Yeah, I don't.
You have it on your calculator.
Yeah, it's negative 1/8. It's negative 1/8.
No, e to the negative 64 is a really small number.
It's like, I think my calculator just basically rounds it up then, because
I see, because e to the negative 64 is too small.
it would be like 0, 0, 0, 0, 0, 0.
Right, I see.
So like the 14th power, so it just kind of rounds it.
Yeah.
It's basically 0.
Yeah, we can, yeah, this is the negative coefficient. Right, pretty much a 0, right? Yes. That makes sense. All right, so since the e to the negative 64 is so small that it's pretty much 0, and the process ends up being negative 8
Yeah.
e to the negative 8x, which equal to negative 1/8, because that's pretty much 0. And then we divide both sides by 8, by negative 8. We cancel the negative. Cancel the negative, you have 8 e to the negative 8x, which equals 1/8. And then we divide both sides by 8. Then you have e to the negative 8x divided by 8. This is going to be 1/64. Right? You divide by 8, so the 8 adds to the denominator. And then we are at the part that you have to get rid of the e, right? The opposite of e is the logarithm. So then we have remove the e, we take natural log of both sides of the equation, which comes like this: ln of the left equal to ln of the right. Ln of the left, ln e equal 1, so this left side is negative 8x. Ln and e are inverse function. Cancel each other, so the input is negative 8x. The right side is ln of 1/64. And when you have 1/, it's negative 1 power, negative 1 to the front. This is actually negative ln of 64. If we cancel the negative on the left and on the right, then we have 8x equal to ln of 64. Solve this further, you divide both sides by 8. You can out of space. Let's move it over here. So x is equal to ln of 64 divided by 8. Right, it's all the algebra. Thank you. So answer the question and goes ln of 64 by 8. The denominator is 8, but it doesn't cancel the 64. The 64 is locked or locked in by the ln, and it doesn't cancel out. So you can't cancel any number. It's not a multiplication, so that's the only value we find out. That's the answer. Any questions? At least that's after we work out the algorithm. It does involve a lot of treatment in between the logarithm function. Kind of problem. Any question? If you have any question for your version of it, please mention us. We can work on. So this is another mean values here. So we have mean values here. Strict function, I think it was cosine. We have mean values here for polynomial, mean values here for the control function. This is a practice question that I was going to do today. All right, this is a polynomial. I type it up as x to the power 3 minus 2x to the power 2. We choose the interval 0 to 2, and let's find the c in the mean values here. So let's see if you can find the answer without. Oh. Okay, thank you. Thank you. My C version. Yes. Oh. The function value actually equals 0, right? The f of 0 equals 0. Plug into actual equals 0. So 0 equals 0. So the average, the mean value equals 0. So we're trying to find now we try to find the point when the derivative equals 0. So we're solving the derivative equals 0. I can write it over here on the board. Right, we got our interval 0 to 2. That's our A and B. So alpha A, which equal to alpha 0, 0 and alpha B, which equal to alpha 2, that also equal to 0. So you got alpha B minus alpha A over B minus A, which is 2 minus 0, 0 minus 0, that's 0. That's really the step 1. And then step 2, we are supposed to find the derivative. Derivative of the function is 3x squared minus 4x. That's 2x squared, so the derivative is 4x. And then the last thing is to set them equal. Have 3x squared minus 4x equal to 0. And you can factor out the x. You have 3x minus 4 equal to 0. This is the factor, so it has to be equal to factor equal to 0. You have x equal to 0. And then you will have 3x minus 4 equal to 0. Now x equal to 0 is in the middle. It's in the edge of the interval, not between them. So that's not what we're looking for. This is 3x equal to 4, and then x equal to 4. 3. That should be the answer. The derivative equal to 0. Or you can graph it. If you graph the whole function between 0 and 2, you can see where the tangent line is horizontal. 0. So this is 4. Anyone else? Right, so the answer should be D is 4. So it should be any other questions? All right, if not, let me start a little 3.3. Chapter 3 work on the application of derivatives. So we talked about section 1, we're using derivative to find the maximum value and minimum value on a closed interval. And section 2, we're looking at mean value theorem to find out special point with the slope equilibrium slope, mean value of the slope. Now, 3.3 is, the title is called increasing and decreasing function. So we're really focused on the actual meaning of the derivative. Whenever the derivative is positive, the function will be increasing. When the derivative is negative, and the function will be decreasing. After we figure out the increasing, decreasing, not only do we know the increasing, decreasing interval, we will be able to determine the maximum mean for the overall function. So if you study the increasing, decreasing behavior of a function, we're not limited by the interval anymore. You can look at from negative infinity to positive entire domain. What's the function behavior? All right, so before that, let's talk about the definition for increasing and decreasing. So in section 1, we define what is being called maximum value, what is being called minimum value. Now this section, we're going to officially define what is being called an increasing function or increasing interval for the function, and what's the decreasing interval. All right, so suppose we got a function, the function is defined on the interval I. Okay? So we would say the function is increasing on the interval if for every two-paired number, the smaller x value always being matched with the smaller y value, and the bigger x value always is matched with a bigger y value. And that we would say the function is increasing. And we see the function is decreasing on the intervals if for every pair of number a and b, and a is smaller than b. We do this because we are trying to pair the left and right. Smaller number on the left, a bigger number on the right. They always end up having smaller x have a bigger y, and bigger x has a smaller y. Then this function must be decreasing. So visually, try to put recording. So if I want to record it, I probably should do it here. So visually speaking, think about those x value and y value match to like this. Because we almost always identify one letter for the smaller x value, one letter for the bigger value. So the increasing means here is A, here is B. This is a number line. The one you will write on the left will always be the smaller. So this is a smaller x, and this is a bigger x. Now, for an increasing function, it goes like this. Doesn't matter what's in the middle, but this is the y value for A. This is the f of A, right? And this is the y value for B, f of B. So you always see that a smaller x is paired with smaller y. Bigger x is paired with bigger y. That's what we call an increasing function. Now, decreasing function looks like this. We still have A and B. A is on the left, B is on the right, because A is smaller. But the f of A and B are bigger, so it's like this, right? Because the smaller A, smaller x has bigger y, and the bigger x, which is B, has smaller y. And that's decreasing function. And if the function is increasing only, or if the function is decreasing only, they're called monotone, right? Monotone function. If the function is not monotone, meaning that the function is sometimes increasing, sometimes decreasing, then we should look at scale, like make the interval smaller. So they're actually monotone individual interval. And then here for increasing, decreasing, we allow them to be at some part being being equal. But if we remove the equal sign in the definition, they're being called strictly increasing and strictly decreasing, meaning that at no point this is actually strictly increasing. So it doesn't involve any recovery. So for example, sometimes the function, like the Q function, it looks like this. So for example, the x here, right? You can see it's strictly increasing here, strictly increasing here, but right now there, and that's one of the points. It seems to be the function tends to be falling a little, not exactly. So I would say it's still increasing. But to be strictly increasing is slightly higher requirement on function. Right. So definition for increasing and decreasing. So now let's try to relate that to the derivative. If the function is continuous on the interval a to b and it's differentiable on the open interval a to b, then we will see the function is increasing on the interval a b if the derivative is positive for all the points in the interval. If the derivative is negative, then it's called decreasing function. And we mention this all the time because derivative represents slope, right? If the slope is all positive for every point in the interval, then of course it's increasing. If the slope is negative, then it's a decreasing function. Now, if the slope equal to 0, then the function is constant. Any question? Okay, so then, so obviously derivative provided a quick way to identify increasing and decreasing, or even when the critical points. The derivative become more useful once we have clear understanding of the geometry. All right. So we're gonna have a couple of exercises. We're gonna try to find out the interval on which the function is increasing or decreasing. Meaning will mean a function that's randomly defined is sometimes increasing, sometimes decreasing. We have to find out the derivative and look at where is that derivative zero or undefined, because those are the points that separate the increasing from the decreasing. So we have to analyze the function. So here is a plan. Take any function, and in order to find the interval for the function to be increasing or decreasing, number one thing is we find the derivative, and then we're going to find the set of derivative is either undefined or undefined. But if undefined or equal to 0, we'll find the critical point. And those critical points are going to behave as a divider. So we're going to look at the whole domain of the function, and we're going to identify the critical point. And those critical point is going to divide all the entire domain into small intervals. And on each interval, we're going to find out if it's positive or negative for the derivative that we know is equation. So that sometimes I'm calling this process as the sign analysis of the first derivative, because we're analyzing where is the derivative positive or negative. So let's look at the process. The question is to find the interval on which the function is increasing or decreasing. So we are focusing on the behavior of the function in terms of the interval. Whenever we talk about interval, we're mentioning the x value. So we're looking at the horizontal number line, the x-axis of the behavior. Right, if we try to separate them into steps, so step 1 is to find the critical point, step 2 is identify the interval, step 3 is determining the sign analysis. Right, let's find the critical point. To find the critical point, we have to find its derivative. Right, the derivative of the function is equal to 3x squared plus 2x minus 1. The whole reason that we're doing it is to find critical points. There are two kinds of critical points, two kinds of possible values. Is when the derivative equals 0 or defined. Right, but this function is a polynomial. It is always defined, always well defined. So if we don't have any undefined point, so now the only thing we can do is set it equal to 0. 3x squared plus 2x minus 1. Let's see if it goes 3, 2, 1, right? If it's 3, 2, 1, I can see how it's being connected, so I'm guessing it's factorable because 3 minus 2 minus 1 equals 0. So I know there is an integer solution. If I cannot factor, I'll probably go by quadratic polynomial right now. So we will have x times 3x. That's the question. That's the factoring of the degree 2 term. 3x squared equal to x times 3x. And I'm going to factor the negative 1. Negative 1 can be factored as negative 1 times positive 1. Really, there's not a lot of factoring way to factor it. So let's try to see if that works. Negative 1 and positive 1. Right? It didn't work, right? If you do it this way, then the negative 1 has to multiply 3x. This x multiplied by 1. You can combine this negative 2x. We want a positive 2x. So we kind of have to switch the sign. So maybe this one should be positive and this one should be negative. And that works out. Right? Any questions? It's called a trial and error. You try it, if it doesn't work out, you switch the sign or switch the number. So this works out okay because the negative 1 times positive 1 is negative 1. In the meantime, this to multiply is 3x, this to multiply is negative x. 3x plus negative x is 2x. So now we get the factors. So we have that x plus 1 equal to 0 is 1 possibility for the product to be 0. This is a multiplication equals 0, one of the factor equals 0. The other factor is 3x minus 1 equals 0. All right, so we're able to separate from big equation into two smaller equations, and the smaller equation has lower degree, it's easier to solve. This gives you x equal to negative 1, this negative 1 plus 1 equals 0. This one gives you 3x equal to 1, move the 1 over to the right, and then x equal to 1/3. So we find two numbers. Any question? All right. A polynomial has a domain, which is the negative infinity to positive infinity. Step 2, we're trying to determine the interval. the question says find the interval on which it's increasing or decreasing. So you gotta know what interval, where are the interval. So in second step, we try to construct the interval, and an interval is really part of the number line. So what you can do, you draw the entire number line. So the whole number line goes kind of like the x-axis. On the left is smaller, it's negative infinity. On the right is positive infinity. We find two critical points, and we're going to have to put the smaller one on the left, which goes -1, and bigger one on the right, which goes 1/3. Okay, these two numbers are like the divider or separator. It's kind of cutting the whole number line into 3 pieces. All right. So now every piece here is an interval. So the first interval is from negative infinity. You can see it's really part of the number line. Negative infinity to -1, the first interval, and then -1 to 1/3. That's the second interval, and then 1/3 to the positive infinity. That's the last interval. This is how we construct the interval from the critical point that you saw in step 1. So step 1 is kind of important to affect is how you construct the interval. Step 2. Any question? All right, now we need to know each interval, is it increasing or is it decreasing? Because the critical point are the only point when behavior change. Each one of the interval, it is either increasing or decreasing. It cannot be both. Because right, if it did change increasing, decreasing, you would have a critical point there, but there's no more critical points, and these are only possible changes. All right, so step 3, since we're talking about increasing, decreasing, step 3, we're really gonna talk about increasing, decreasing. Let's call it step 3. Right, so I like to use a little arrow. This is up arrow, which represents increasing, and down arrow, which represents decreasing. So we're going to mark out increasing, decreasing on each interval. So how do we know it's increasing or decreasing? Make the first interval. You pick a special point in the middle of that interval just to test it. For example, between negative infinity to -1, there's -2. So I'm using a -2 as a testing point. So let's find the derivative function's value. The derivative at -2, which is equal to, remember the derivative tells you increasing, decreasing, right? I'm going to calculate it and see if it's positive or negative. So you're gonna, that's our derivative. So you're gonna do 3 times -2 squared plus 2 times -2. And then -1. The square makes the negative number positive, so this is actually 4. 3 times 4 is 12. So 12 minus 4 minus 1, that's actually equal to 7, which is positive. Okay. So we know that first interval, I pick one point just to make an example. You can pick any other point. It's guaranteed on the entire interval. Any point in here, the derivative will be positive. So what's really important is it's not the 7, it's that the fact that it's positive. Are we okay? So we know on the first interval it's definitely increasing. So this interval we have increasing. I'm putting the arrow there just so I don't have to write the word increasing. All right, and then the second interval is the interval between -1 and 1/3. -1 is negative and 1/3 is positive. It's right in the middle. There's a special value, which is 0, right? 0 is between these two. So we're going to test the derivative at 0. Looking at 0, and we put in 0 here, and then you see it's going to be -1 because 3 times 0 plus 2 times 0 is 1. So this is a negative whenever the derivative is negative. I mean, on the entire interval, they should be the same. I just picked any number to test it. Any questions so far? So we know it's decreasing, right? This interval is decreasing. This is increasing, it's decreasing. So the function goes like this. This degree 3, right? The function would be increasing, then decreasing, then increasing. That's exactly how cube function is behaving. That one was the -1. Remember, like this is -1, this is 1/3. But I'm not sure about the y-axis. So it's probably this is just a sketch of the picture, not the exact picture, but at least we kind of see where everything is going. All right, so that's the second interval. It's decreasing interval. This interval is a decreasing interval. So we want to find the interval on which the function is decreasing or decreasing. So last one, and let's see if it's increasing. So we pick a number. 1/3 is a fraction. We pick an even number. Let's pick 1. 1 is bigger than 1/3. So we do f prime of 1. You can pick any number. You can pick 2. I mean, any number. So plug in 1 made it easier to calculate. So we get 3 plus 2 minus 1. That's 5 minus 1, which is 4. 4 is positive, and the function is increasing on the interval. So now we kind of confirm that the this function is increasing, then decreasing, then increasing on those 3. Any questions? So to answer the question, the interval where the function is increasing, they are -infinity to -1 and 1/3 to +infinity. That's the interval where the function is increasing. The interval where the function is decreasing is from -1 to +1/3. So that's the answer to the question after we went through the analysis for the first derivative. Any question? So this is our first example. All right, let's talk about something it's called the first derivative test. As you can see, what we can see here in the first example, if the function was increasing, then decreasing. This is when the derivative is positive. Decreasing is when the derivative is negative. Right here, you have a maximum, a local maximum or relative maximum, right in the middle. It's cannot guarantee. I mean, Q function goes increasing further ahead if you expand the view. But when you zoom into that single point locally, that point is a maximum value, right? So that's what we are going to do. Like after you understand the increasing and decreasing, you're able to identify some local behavior. For example, here it's decreasing, then increasing. The derivative will be positive. This point would be a minimum value, at least in a small interval. Local behavior there. So that's what we're talking about. It's called a first derivative test. Sometimes we want to tell after you find the derivative and then you determine the critical point. At the critical point, you ask yourself, do I have a minimum or do I have a maximum? Or it's not in any of them. So according to what we say, if the function switch from positive to negative, which goes increasing and then decreasing. Right there, you have the relative maximum, like this one, right? Decreasing, increasing, and decreasing. That you have a maximum. But if the function's derivative switch from negative to positive, meaning it goes decreasing, then increasing, you have a minimum. It's called first derivative test because we're using first derivative to tell whether we have a maximum. Lastly, if the sign of the derivative did not change, you go positive, 0, and then positive again, kind of like the Q function, then of course there's no minimum or maximum since the function is not the relative minimum or maximum. So by looking at the sign does not change at all, and therefore we do not have any special, any extrema at around that point. Any question? This is called the first derivative test. So often after we determine the sign, we finish determining the increasing, decreasing, we can quickly identify max and mean, or at least a relative max and relative mean. This question, find the interval where the function is increasing and decreasing, and then use the first derivative test to determine if we have a relative maximum or relative minimum. So I do it one more time. Do the same process as what we did with the first example. All right, so we're gonna do, first we have to find the critical point. So step one, determine the critical points. To determine critical point, we have to find the derivatives. Values. Okay, to do that, we're gonna find the derivative. This is a division, we have the proportion rule. We will square the denominator. And then in the numerator, you will find the derivative, which is 2x, multiplied by the denominator. Minus this time, we're keeping the numerator. We're going to find the derivative of the denominator, just the denominator has the derivative of 1. So that's what we have. And then the numerator will then be 2x squared minus 2x minus x squared and minus 3. I have to expand it because I need to find the 0. Right? So now this function is different. This function has a division, so the domain of the function, I'm not drawing the whole number line anymore, because according to this function, x cannot equal 1. So the number 1 is not in the domain. So the actual interval you were drawing already has this 1. Right. You will be having an invisible wall at 1 because the 1 is absolutely not allowed to be the x value, right? If x equal to 1, they will be undefined. Are you okay there? So 1 is separate in your graph. Your graph will have a complete separate piece on the left and then another piece on the right. So visually, you have separate apart. They're not going to be connected functions. If the function has a discontinuity at 1, separate them. And therefore, we don't have to worry about the denominator equal to 0 because x minus 1 are not allowed to be 0. We don't have any undefined point. This is a fraction, so if you want to find a critical point, and you got a fraction, for the fraction to equal to 0, the numerator has to be 0. So if we want to make at prime equal to 0, right? If it equal to 0, then the only thing we have to worry about is the numerator. So we have 2x squared minus 2x minus x squared minus 3 equal to 0. Now we can combine the x squared. It's x squared minus 2x minus 3 equal to 0. This is being factored into x minus 3 and then x plus 1. Okay, so then again, we have x minus 3 equal to 0, which means x equals 3. And then x plus 1 equal to 0, which means x equal to negative 1. So those are the two critical points. And now we finish with step. Any questions? All right, now we're moving on step 2. We're going to try to determine the interval. Okay. And what point did we find? We find a negative 1. This is positive 1. And we have a negative 1, which is on the left of that 1. And we have a positive 3, which is on the right of that 1. I mean, this 1 is separating the whole picture, right? It's a domain thing. So now we're going to look at what interval do we have. So here we have this is negative infinity on the whole number line. Right, so the interval goes, the second step 2, we're trying to determine the intervals. Right, so interval is part of the number line. So we go negative infinity to negative 1, and then negative 1 to positive 1, and then 1 to 3, and then 3 to positive 3. Any question? As you can see, within a 10, we have to consider the 1 there because x is not equal to 1. So you draw your number line to the domain, make sure you get rid of any undefined point for your original function. So that's step 2. We now have our interval. Follow our plan. Step 3 is now for each of this interval, we're going to find out whether the function is increasing or decreasing. And what do? We pick out random point in that interval to make a test with our first derivative. So for example, the first interval from -1, negative to -1, we pick any point. To make it easy, we pick a point such as -2, the left prime of -2. That we're gonna calculate from here. The numerator can be combined. Let's combine that one with that one to x squared. So it's this one where x minus 1 cubed. So calculation goes -2 squared minus 2 times -2 minus 3 over -2 minus 1 cubed. Well, it was square, right? It was square. It's like, I was copying the cube and then I realized I can't write. Somehow I copied over into a cube, even though it's supposed to be a square. So this is square. This is equal to, the denominator is -3 squared, this is 9. The numerator is 4 plus 4 minus 3, which is 5. So it's 5 over 9. Whatever the number is, you can use your calculator to confirm it, which will be a lot faster than what I did. Just want to know this is actually positive. Now, because the derivative is positive, the first interval is increasing. First interval is increasing. Now let's look at the second interval. It's between -1 and 1. What number do I choose for the test?
0.
0. So it's 0 is between -1 and +1. So we're going to find out f prime of 0. If those x are 0, the x's are 0, then the -3 is the numerator. This is 0, so 0 minus 1 squared, that's 1, right? -1 squared is 1, so this is a -3, which is negative. Whenever the derivative is negative, it's decreasing. So this is decreasing. And then we have an asymptote. This is a separator from 2 parts. So here it's not going to go continue. It's going to go all the way down. It's going to go decreasing to infinity to negative. So it's increasing this. So you should see a graph that goes up and then way down. And that's the behavior in that part. Moving on between the 1 and 3, we pick the value 2. Plug into out of space over here. F prime of 2. We put in 2 for the x value, so the numerator will be 4 minus 4 and then minus 3. The denominator would be 2 minus 1 is 1, so it's 1 squared, so it would be 1. So then that's -3 actually, so it's increasing. So on this interval it's increasing, right? So it has to decrease from, see over here, it's decreasing, but there is that asymptote. It goes this way. So on that side, it must be decreasing from the infinity and then reach to a finite number. All right, and then we can see the last interval is 3 to infinity. We pick a number such as 4. And now we have to calculate, maybe I choose different color to make it visible. Let's calculate the derivative at 4. We're going to put in 4 there, so it's 16 minus 2 times 4 minus 3 over 4 minus 1 squared. So the denominator is 9 and the numerator is 5. It looks like symmetric. So it's positive, and therefore on this interval is increasing. So now we know the increasing interval for the function is from -infinity to -1, and from 3 to infinity. The decreasing intervals from -1 to 1 and 1 to 3. They're all open interval. So that's the first question. Find the interval on which the function is increasing or decreasing. And then we're going to use the first derivative test to determine whether we have a relative minimum or relative maximum. This is continuous. That point is continuous, so this has increasing then decreasing. So at -1 we have a relative maximum. And over here at 3, we're trying to find the x value is this is decreasing and then increasing right here. That at x equals 3, we have a relative. The answer to all the questions. Any question? That's the first derivative test. The graph is really a rough sketch, and you want to determine, confirm what we have here. We can use a actual expression: x squared plus 3. So x plus 3 divided by x minus 1. So this is what it actually behaved. So we have a increasing, then decreasing to infinity, decreasing, then increasing. So we can see that our picture did show the increasing, decreasing behavior, but because we didn't calculate any y value. So from here, it looks like they could be achieving the same value, which they did not. This is a way lower than this. This is way higher than that. All because we didn't calculate y value, we only calculated x value. So we have the right behavior horizontally, but we don't have the right height. So y value. And this answers all the questions in this example. Any questions? So this, but it does show very clearly how to identify using the sign of the inverse derivative. Right, one more example if we have time. Right, let's do one more example, and then we're probably going to do more practice questions tomorrow. And this skill, I think, is really useful because even if you're studying something else, as long as you find out the rate of change, you can draw a similar graph of the timely behavior, decreasing, decreasing. It made it possible for you to analyze, like in the long run, time-wise what's behavior. Right, this function we're going to find the interval where it's increasing, decreasing, possibly identify the relative minimum or relative maximum. So similar to the previous question. The only thing that's extra in here is we have fraction in the exponent. When the exponent is not integer, it means that this is no longer polynomial. We actually have roots. This is a cube root. There is 3 in the denominator of those fractions. So now the power form, right now is power form. The power form made it easier for us to find the derivative, but you still have to know the actual meaning of it. Write it back to root form in order to find the critical point. So step 1 is to identify the critical point. So we want to find the critical point. All right, critical point is when the derivative is equal to 0 or when the derivative is undefined. But whichever one you want to find out, you first have to know the derivative. And we apply power rule. You move the power to the front and then power minus 1. 8 over 3 minus 1 is 5 over 3. Because a minus 3 is 5. And then the 4 times 2/3 is 8/3. Right? If you multiply 4 with 2 over 3, the multiplication happened to the numerator, so 4 times 2 is 8, so 8 over 3. Multiply the power, and then the power has a minus 1, so 2/3 minus 1. 2/3 is a fraction, 2/3 minus 1 is negative 1/3. That's what we have. So after we find out the derivative, we kind of have to write it back to the original meaning in order to solve we do. And I think it has undefined point because if you write it, this is 8/3. I'm factoring the 8/3 out. This is x to the power 5. The 5 in the numerator is a power. The 3 in the denominator is a root. So we got cube root of x to the power 5 minus, I bring the 8/3 to the outside. So minus 1 over, and then we have a cube root of x. So this is a practice of converting from the power form to the root form. And sometimes we convert from root form to power form. I write it this way because we can see that we actually have an undefined point. In the original function, the power are all positive, so the x value can be any x value. But now we have 1 over root of x. So this x is not allowed to be 0. So x equal to 0 is a undefined point, but it's not an undefined point for the original function. In the original function, your domain goes negative infinity to infinity, and that's where we do the number line. So anyway, f prime is undefined when x equal to, I'm trying to write here, when x equal to 0. So that's 1 points already. All right, and then the other one is, the other kind of critical point is when the derivative equals 0. So if f prime equals 0, it's also a critical point. So now we're going to set it equal to 0, which I did already. So I'm setting this equal to 0, and that's where we're solving the critical point. And you see the 8/3 is a common factor. You can divide that out, or you can think of that one as a factor that doesn't equal 0. So this part are equal to 0, right? Only the part that has variable, now that you factor it out, divide out the 8/3, and then now we have this part got equal to 0. That's what we're solving now. All right, there's only 2 terms on the left. We move it to the right, and this is the nice part about this is once you move it, oh, it's already 3:15. It looks like we're probably going to come back to it tomorrow. But let's finish it tomorrow so I don't eat up your time. I'll see you tomorrow to finish. Yes, I'll open up the homework so we can practice.
Like, you mean like before?
Yeah,
This afternoon?
right after class.
Oh.
Yeah. Thank you. Let me finish this tomorrow. And the attendance question, if you came in late, the attendance question.
Thank you.